But what's SEM? What's a structural equation? What's the meaning of structural equation modeling? A structural equation modeling actually called the second generation of data analysis. It's called second generation of data analysis, right? And contrary to first generation of quantitative data analysis technique, like regression, like correlation, and other technique that we discussed so far, SEM or structural equation modeling work with there are two characteristics of second generation or SEM that actually distinct this method or second generation from first generation. Second generation, different with the first generation, can work with the latent variables, right? You remember for multiple regression, when we have a few variables and each variable measured by some items. For example, in your assignment, you have community attachment, you have economic gain, and you have, for example, positive perception toward tourism. And each construct is measured by some items. Community attachment is measured by 4 or 5 items. Economic gain is measured by 4 items, and positive perception also is measured by 4 or 5 items. So to run multiple regression, what we need to do? First, we need to calculate the value or score of variable, right? So to include community attachment, to include economic gain or positive perception in regression model, in regression equation, first we need to calculate the score of this variable. So before going to perform regression, we need to create a new variable. And this new variable is a score of, for example, community attachment. So you get the average of 5 items of community attachment and create a new variable based on average of 5 items. This happened for all variables, right? So before starting analysis, before starting to perform regression, you need to calculate new variable. You need to compute new variable. And these new variables are average of items. So you cannot work with items. You need to transfer these items together to a new variable called community attachment and use this new variable for your analysis, right? But in SEM, no need to calculate actually community attachment score, no need to calculate the other latent variable score. And you can use items, you can use indicators. And actually by connecting indicators to construct or variable, connecting items of community attachment to community attachment and other variables, other items to other variables, you can actually perform your analysis. So the main difference between first generation and second generation is able to work with latent variable and no need to calculate score before analysis, right? Another main difference between first generation and second generation is second generation can work with and can be performed for model with the different level of complexity. So, for example, if we have 3 different layers, some antecedent influence on dependent variable, and this dependent variable also influence another dependent variable, still we can run second generation or SEM. But in first generation, you remember, for example, for multiple regression, only we have performed two layers, one independent variable and one layer of dependent variable. And also dependent variable can be one for multiple regression. For t-test, only we have 2 variables, one independent and one dependent variable. For correlation, we have only 2 variables, one IV and one DV, right? If we can call IV and DV, but IV and DV is mostly used for regression, right? So we have 2 layers. But in SEM, we can have different layers of variables, and we can run all whole model concurrently, simultaneously. So we don't need to split different layer to run analysis, right? For example, okay, let me draw something here. For example, if this is one variable, x1, x2, x1, x2, and this is x3. These 3 affect on y. You can see my drawing? Yes. So effect on y, and y effect on z, for example. And you have another variable here, w. This y effect also on w, and this x3 also effect on w. So if we have this framework with the 3 layers, right? So it's not possible to run this model, to perform this model in using first generation. For first generation, we need to actually see the relationship between these 3 and y, one model, right? Y on z in another model, y and x3 on w. This is another model. So in first generation, we need to run this model 3 times and in separate models. But in second generation of analysis, we can run whole model with any layers and any level of complexity simultaneously all together, right? So this is another main difference between first generation and second generation of analysis. Okay, for example, here we have X and Z influence on Y. So this seems a simple model, but still for this simple model, we cannot run together. We need to run one time X and Z influence on Y, effect on Y, and another time Z effect on X. So this is 2 main difference between structural equation modeling and the second generation of analysis technique and the first generation techniques. So there, these 2 are 2 main difference between first and second generation. In social science, most of time we actually work with latent variables, right? We before discussed that most of time our variable in social science is either reflective or formative latent variable, right? So we have actually the latent variable in our framework when we measure attitude, when we measure satisfaction, when we measure belief, when we measure, for example, intention to purchase, when we measure loyalty. So these different types of variable that we are working in different disciplines in social science, most of time are latent variable. And most of time we have complex relationship between variables. So based on these two reasons, first generation is not suitable for most of studies in social science. And we need to apply second generation and structural equation. So this is two main reasons to apply SEM. Here is an example for example, when we have a latent variable. We discussed before this error term, if I'm not mistaken. For example, we have reflective latent variable. For reflective latent variable, you know, if I reflect, okay. For reflective latent variable, we have, for example, here three items. The three items reflect the meaning of the construct. So you can see these three items, x1, x2, and x3, includes two parts. One comes from construct or latent variable, and another part is error term. So this x1 that we measure actually in our questionnaire, x1, x2, and x3 are questions or items that we measure in our questionnaire to measure construct. For example, satisfaction. We ask three questions to measure satisfaction. So these three questions include two parts. One part is a real part that reflect the meaning of satisfaction. But there is another part that is error and is not actually part of this construct, doesn't reflect the meanings, some part of meaning of this construct. So we have these two parts. But when we apply first generation, actually we ignore these error terms. And we consider these error terms exactly same for all these items, right? So we actually create an error in all results when we calculate score of latent variable and we get average of latent variable. Average of to calculate score of latent variable based on average of items. So we ignore these error terms, right? So when we ignore these error terms means we create an error for the meaning of latent variable. And this error influence on result of a structural model, result of multiple regression. How? Because actually the score of satisfaction is not real score of satisfaction. It's different with score of satisfaction, right? So here, when we, for latent variable, when we apply first generation, actually we ignore this error. We ignore these error terms. That this error can come from random error or systematic error. So there are different sources for this error, but this error exists. But when we use average of these three items to calculate a latent variable score, latent variable value, So we ignore these error terms, right? So for a latent, using first generation for latent variable, actually we skip and we ignore this error term. Okay. So compare first generation and second generation. Traditional method, first generation work with observed variable. And if we don't have observed, we create observed. When we calculate the community attachment, actually we create observed variable based on average of items. Okay. So, but using structural equation modeling, we need to understand some new concept and new definition. Because definitions in structural equation modeling is a bit different with first generation. There are a few main differences between concept in first generation and second generation. One of the main is name of variables in first generation and second generation. In first generation, we use independent variable and dependent variable, right? Independent variable are some variable that influence on other variable. And dependent variable in first generation are variables that are influenced by other variables, right? We have two, right? So this layer is independent variable, right? And this layer is dependent variable in first generation. But in second generation, we don't use IV and DV. Why? Okay, in second generation, for example, we have another layer here. This is Y, Z, X1, and X2, right? Okay. For first generation, this one was DV because we don't have this layer. But in second generation, we don't call this variable or this variable DV, and we don't call this variable IV. We use exogenous and endogenous latent variable, or exogenous and endogenous construct or variable. Exogenous variable is a variable that no other variable pointed to this variable. Okay? For example, X1 here. There is no other variable that pointed to X1. Here, before this variable, we don't have any other variable. So these two variables called exogenous variable. Exogenous variable. These two variables. Because we don't have any other variable that points to this variable. But endogenous variable is some variables that there are some variable before that. There are some variable that pointed or connected to this variable. For example, Y and Z. Y, X1 and X2 connected to or pointed to Y. Z, Y pointed to Z. Right? So we have another variable that affect on endogenous variable. So these two variables called exo or exogenous, and these two variables are endogenous variable. Exogenous variable is something similar to independent variable, but not exactly the same. And the endogenous variable is somehow similar to dependent variable, but is not the same. Because, for example, for this relationship, this can be DV, but for this relationship, this is IV. So we don't use IV and DV anymore in SEM. And we use exogenous and endogenous latent variable. So this is one difference in definition of and concept that we use in SEM. Another one is inner model or outer model. Inner model and outer model, or a structural model and measurement model. Okay, here. Before going to inner model and outer model, here exogenous and endogenous. These two variables are exogenous, right? Because there is no other variable that pointed to this variable. And this variable, ease of use and usefulness. But attitude is endogenous because these two variables influence on attitude, right? So this one is endogenous. Okay. Inner model and outer model. Outer model or measurement model, these two concepts can be used exchangeable. You can use either outer model or measurement model. Outer model or measurement model refer to relationship between items or indicators of each construct and its variable, its construct, its latent variable, right? So the relationship between indicators, the relationship between items and the construct and latent variable called measurement model or outer model. So when we talk about measurement model or outer model, actually we refer to within a construct. Within a construct, inside a construct. Inside a construct means how items measure this construct. Okay, here, ease of use. Ease of use. Ease of use is measured by 5 items. So when we talk about the relationship between these items and ease of use as a latent variable, so we refer to this one. We refer to this one, right? So this is outer model or measurement. When we discuss items of usefulness, so relationship between items and construct, usefulness, this one, we refer to measurement model or outer model. And also here, attitude is measured by 5 items, 5 questions, 5 indicators. So when we talk about when we talk about items of attitude and this construct, this refer to measurement model or outer model, right? So this is the meaning of when we say measurement model, when we say outer model, we refer to items of each construct. And for measurement model, we need to assess reliability and validity to see these items are reliable and valid items to measure this construct or not, right? So this is the meaning of outer model or measurement model. But when we refer to relationship between variables, relationship between variables in our framework. For example, relationship between ease of use, usefulness, and attitude. This one. This relationship is inner model or a structural model. Inner model or a structural model. So in SEM, when we say outer model or measurement model, we refer to relationship between items and construct, items of each construct. When we discuss inner model or a structural model, we refer to relationship between variables, right? Between variables. For example, here, we have another model here, right? Okay. Anybody can say where is measurement model and where is structural model for this one?
I have a try.
Yes.
Indicator x1 and 2, x2, x3 to it is called yes, this part, and x4, 5, 6 that part, and the third, and y1, y2, y3. These three parts are called outer model or measurement model, but the relationship between these yes is called inner model.
Or a structural
construct.
Exactly. But for these three variables, this construct is, you can see the direction of arrow.
Formative. And reflective, right?
Yeah, exactly. This one is formative. So measurement model of this construct, this latent variable is formative, right? But this one is reflective, and this one also is reflective. So here we have measurement model, one formative measurement model, and two reflective measurement model or reflective construct. But this one refers to inner model and structural model when we talk about variables. So based on what we discussed before, hypothesis refer to measurement model and or a structural model. Which one? Hypothesis refer to measurement model or a structure?
Structural model.
A structural model. Because hypothesis is relationship between variables, right? Between constructs. So hypothesis is for a structural model. But for measurement model, we need to assess measurement model based on some criteria. As measurement model is a relationship between items and construct, for measurement model assessment, we need to check reliability and validity, right? We need to check loading. You remember in factor analysis? In factor analysis, we check loading, right? So factor analysis is a way to check the validity, but for a pool of items. A pool of items. So we check validity using factor analysis or EFA when we don't know which item belongs to which construct. But when we know, okay, we need to check reliability and validity of these three items, X1, X2, and X3, to measure this construct. X4, X5, and X6 to measure this construct. And Y1, Y2, and Y3 to measure this endogenous construct. These two are exogenous and this one is endogenous, right? So again, inner model refer to, or a structural model refer to relationship between variables, and measurement model or outer model refer to relationship between items and construct. For these two, for measurement model and structural model, actually, we need support in the literature, and we need support from the literature. So in SEM, we say we need two types of theory: measurement theory and structural theory. Measurement theory means we need to have support that why these three items measure this construct. Why these three items, x1 and x2 and x3, measure this construct? Why? So we need to find support from the literature that these three items are suitable to measure this construct. And x4, x5, and x6, why these three measure this construct? So we need support, and why these three measure this construct? So this one, we need support from the literature, and this called measurement theory. So we need measurement theory to support items of each construct, items to measure each construct. And we need a structural theory. A structural theory is to support this hypothesis. For example, if this hypothesis and the relationship between this variable is h1 and this one is h2, right? For example, this one is attitude, this one is subjective norm, and this one is intention, right? Intention to purchase. So when we say attitude has positive effect on intention, H1, we need theory to support this relationship. When we say subjective norm has positive effect on intention, so we need the support, we need the theory to support H2. This theory that support a structural model called a structural theory. Right? So we need two types of theory. We need two types of support from the literature. Support for measurement model and support for a structural model. Right? Measurement theory and structural theory. Okay? Is it clear? Okay. So this is the definition of measurement model or outer model, and a structural model or inner model. Reflective and formative we already discussed, so just skip. Just very fast, very quick review of reflective and formative. If you remember, for reflective, the direction of arrow is from construct to item. So we have error term in item level, and the equation for each item, the relationship between construct and item is this equation, this lambda called loading. Loading. So for reflective construct, we measure factor loading. We measure factor loading, and factor loading should be higher than 0.7, like factor analysis. Like factor analysis. So factor analysis only is suitable for reflective construct. Because in formative construct, we don't measure, we don't assess loading. And assessment of loading is not very meaningful in formative construct. Only is suitable for reflective construct, right? This is reflective construct, right? So for reflective construct, we talk about weight. Here we have weight and weight 1 W1 X1 W2 X2 W3 X3 plus error. And error term is in construct level, not item level. So the value of weight can be low. No need to be higher than 0.7. The value of weight just need to be significant. So for formative and reflective, we talk about different, actually we apply different criteria and talk about different concepts. The main difference in reflective, we talk about lambda and loading, but in formative, we talk about and measure weight and assess weight, right? Okay, and this was an example about reflective and formative that we already discussed. Later I will talk about this one. For reflective and formative, we should be very careful because there are many studies published in very good journals that after a few years, when some scholars evaluate these papers, they found there is misconceptualization for reflective and formative. They actually found, for example, here in this study, they review a very good journal, Journal of Marketing Research, Journal of Consumer Research, Journal of Marketing, top tier journal in marketing. So they found, for example, some items, some construct that modeled as a reflective construct, but should be reflective 65%. But the 31% of these reflective construct actually should be formative. But there were some misconceptualization. And some items that measure formative. 1% should be reflective, but out of 58 construct that are modeled as a more formative construct, 17 of them should be reflective, right? So there are some misunderstanding and misconceptualization for reflective and formative. So you should be very careful to understand the nature of your construct. These are from some paper that published very top tier journal. So you should be very careful for at the beginning of your research for nature of your variable, nature of your construct. Another type of construct that we already discussed is composite. Composite is similar to formative, but we don't have error term in construct level. So formative composite construct is a formative construct that we design. So there is no error term in construct level. There is no missing items to measure formative. You remember for formative construct, we discussed that this measure part, this error part This error part is for missing item. If we have 3 items here and we miss some item to form this construct, this error term represents these missing items. If we have, for example, 2 missing items and we didn't include, we didn't find. So these 2 items are represented by this error term. But in composites, we actually design this construct and we don't have this missing. So actually when we work in SEM, when we apply SEM, for measurement level, for conceptualization of measurement part, we need to be very careful about type of construct. And because of that, we need measurement theory. We need support from the literature to explain what's the nature of items that we apply and what item we can apply to measure each construct before a structural theory. And then based on structural theory, we can hypothesize the relationship between variables. But actually we have 2 main types of structural equation modeling, 2 main types of SEM, right? And these 2 types of SEM can and should be applied for different types of studies. So we need to understand what type of SEM is suitable for our study. Actually, traditional SEM is covariance-based SEM. Structural equation modeling, or it's better to say a covariance-based structural equation modeling, is started in 1970s and developed by a scholar called, namely Jorskog. Jorskog developed the covariance-based SEM and actually Israel software to perform covariance-based SEM. But after that, because of some limitation of covariance-based SEM or limitation of CB-SEM, Jorskog with his supervisor, with his academic advisor, Hermann Wald, together developed another type of SEM. This type of SEM that is developed in 1980 called the variance-based SEM. They developed this variance-based SEM or partial least squares SEM as a complementary approach to CB-SEM. So because of limitation of CB-SEM and because they actually noticed that CB-SEM cannot be applied, cannot be used for all types of studies in social science, different social science disciplines. They developed PLS-SEM or variance-based SEM. And variance-based SEM or PLS-SEM actually has no limitation that covariance-based SEM needs. So we can apply PLS-SEM or variance-based SEM in wider range of models, framework, and studies. So they developed these two techniques, these 2 approaches under SEM as complementary approach, but with different requirements. But actually covariance-based SEM is more popular so far because from the beginning, Carl Jorskog developed a software to perform CB-SEM. But PLSM or variance-based SEM, there was no software to perform until 1990. The first software that was developed to perform PLSM was developed by Wing Chin in 1990. So after that, scholars started to use PLSM. So you can see the history of these two is very, actually, they were born in 1970 and 80, but PLSM was not used in until 1990 because of lack of proper software to perform, right? But after PLS graph software by Wing Chin, developed PLS graph by Wing Chin, a smart PLS software was developed in 2005 and VART PLS software in 2009. So after that, many scholars started to use PLSM. But for application of these two methods, you need to understand requirement for each one. And based on your study, based on the objective of your study and the requirement of your study, you can choose one of them. You need to identify which one is more suitable for your study, right? Actually, covariance-based SEM, also called factor-based or common-based approach. And in covariance-based SEM, there are some criteria very important, like goodness of fit. Because in covariance-based SEM is correlation-based. If we look at correlation, what was the main characteristic of correlation? In correlation, we don't have causal relationship. In correlation, we have bidirectional relationship. So in correlation, we don't say X effect on Y or Y effect on X. We say X and Y are correlated or are not correlated. And we can change, we can decrease or increase together. Right? But PLSM is a regression-based approach. So it's different with the CBSEM. It's regression-based approach. So focus on causal relationship. In contrary with CBSEM. CBSEM focus on correlation or covariance between variables. So this is the main difference between one of the main difference between CBSEM and the PLSEM. The objective of CBSEM is to minimize the difference between covariance matrix, covariance between variables, from data and from model. So in covariance-based SEM, we compare covariance from data and covariance from model and try to minimize differences between these two covariance matrices. Try to minimize difference between covariance from data and covariance from model. So goodness of fit is very important for CBSEM because goodness of fit shows these differences between covariance from data and covariance from model. So goodness of fit is very important criteria for CBSEM. But PLSEM is variance-based approach and try to maximize the difference, try to maximize the explained variance. explain the variance of endogenous construct. Explain variance of endogenous construct. We discussed this explain variance. You remember R square. R square is ratio of explained variance divided to total variance of dependent variable. So PLSM try to maximize this ratio. Try to maximize explained variance of DV or endogenous variable from exogenous variable. So in PLSM, we don't talk about the difference between covariance of covariance from data and covariance from model. So goodness of fit is not important criteria in PLSM. In PLSM, we need to look at explained variance of endogenous construct. So if the objective, so PLS focus on maximizing the variance explained for endogenous, whereas CBSEM focus the model parameter to produce empirically observed covariance matrix and try to minimize the difference between the covariance matrix from data and model. PLSM, because it's the objective of PLSM, the objective of variance-based SEM. PLSM is one of the well-known approach under variance-based SEM. So we use these two terms interchangeably. So we use PLSM and also we use variance-based SEM, right? PLSM is, so the objective is to maximize the explained variance of endogenous construct. PLSM is very suitable for prediction-oriented studies. So when the aim of study is to predict dependent variable, is to predict endogenous construct, so PLSM is preferred approach. Also, PLSM is suitable for theory development. It's different with CBSEM. Because in CBSEM, we try to compare data from, compare covariance from data and covariance from model. So it's suitable for theory testing. For example, if you have exact model that you, other scholars already confirmed this model in other contexts, but you want to replicate this study based on new data in your context, in your case study. So you want to test exactly the same model, but with new data. So the objective of your study is theory testing. You want to test an established model, an established theory in a new context. So the aim of your study is theory testing. CBSEM is preferred approach for theory testing. But if you add some variable, if you combine some theories and develop new model, and you want to actually examine, you want to evaluate this new model, so your work is theory development, model development, is not model testing. For model development, the preferred approach is PLSM, not CBSEM. So the main criterion to choose one of these two, CBSEM or PLSM, is based on objective of your study. If objective of your study is prediction of dependent variable, prediction of endogenous construct, or the objective of your study is theory development, So preferred method is PLSM. But if the objective is theory testing, preferred method is CBSEM, covariance-based SEM. So this is main criteria to choose between PLSM and covariance-based SEM. Also, there are another criteria to choose one of PLSM and CBSEM. PLSM or variance-based SEM are non-parametric SEM. Non-parametric SEM. So they can work with non-normal data. You remember when we discussed first generation and our data was not normal, right? So in SPSS, we had an option to choose bootstrapping or go to non-parametric techniques, right? Bootstrapping actually is something that is applied in, or resampling method is applied in PLSM. So PLSM is a non-parametric approach. So can be applied for non-normal data. So this is another difference between PLSM and CBSEM. But it's not the main reason to choose PLSM. The main reason is objective of your study. Another, actually the difference between PLSM and CBSEM, PLSM can be applied for a complex model. For a complex model. Complex model means you have more than 6 variables or more than 50 items. Or, so this one is very important. Or you have combination of formative and reflective. A few of your constructs are formative and a few of your constructs are reflective. If you have combination of formative and reflective, it's not possible to apply CBSEM. In CBSEM, when you want to apply CBSEM, all constructs should be either formative or reflective. Cannot be combination of these two. So if you have combination of reflective and formative, you have to apply PLSM. And PLSM is a suitable approach for this type of framework. Or if your framework, your model is complex model. Complex model means you have large number of constructs, more than 6, or large number of items. So this is another reason to choose between PLSM and CBSEM. But secondary reason, the first and main reason is objective of your study. Another one also is non-normal and normal data. If your model is, if your objective is theory development and your model is complex, so you can also use another reason to choose PLSM, because PLSM can work with non-normal data. PLSM can work with the smaller sample size. For CBSEM, you need a large sample size, between 5 to 20 times of number of items. But for PLSM actually can be performed by smaller sample size, by 100 sample size. But there are some criteria to actually, I calculate the minimum sample size to perform PLSM. The best is using G-power. Using G-power. Also, there are some other criteria. Before was one criteria called 10 times rule. And 10 times rule means 10 times of number of maximum arrow connected to one construct. For example, is if maximum arrow, maximum variable connected to an endogenous variable is 5. Based on this rule, the minimum sample size could be 10 times of this arrow. So could be, for example, 50. But this threshold and the criterion is no more acceptable. No more acceptable. So we have to choose another criteria. But the general rule for PLSM is can be performed by smaller sample size compared to CBSM. Another difference between, yeah, I think I discussed most of them. So again, the main reason is theory development and theory testing. Second is the complexity of model. If model is complex, PLSM is preferred. Another one is non-normal data and smaller sample size. So these can be other reason to choose PLSM over CBSM. Okay. Here provided some more information about choosing PLSM and CBSM. So if we have a new phenomena to investigate, so new measurement model to investigate. So actually our study is theory development, PLSM is preferred, number of construct and item, again formative and reflective, and lower sample size, smaller sample size, and prediction is the objective of the study.
Prof, can I ask one question?
Yes, yes.
Even if we add one new variable, right, it will become theory development, isn't it?
Yes, yes.
So basically, most of our PhD, it will be based on PLSM. Is that true?
Yeah, I believe.
Okay, all right, thank you.
Yeah. Some other people might not actually agree with me for this one, but based on my understanding, when we actually add a new variable or few new variable in our framework, and we want to test hypothesis, we don't want to actually test an established theory, an established model, covariance space SEM is not suitable to apply. And we need to apply PLSM. Okay, in this table also you can see some difference between PLSM and variance space. This is a paper that we published in 2018 with the, if you know these people, Christian Ringlet and Marco Sarcet. These two are grew in PLS. So we published this paper with these two persons. And this paper was published in the International Journal of Contemporary Hospitality Management. In this paper, actually, we provided a very good guideline for application and reporting of PLSM. Application and reporting of PLSM. So you can use this for criteria for assessment of measurement model. Later I will discuss what criteria we need to apply for assessment of model, assessment of measurement model, and structural model. But this can be a good reference for evaluation and reporting. For CBSM, we have different software. MOS is a very famous software in this area. It's graphical software. L'Israel is one of the first software that was developed by Carl Droskov to perform CBSEM. But this software, L'Israel, is not graphical software, so you need to be familiar with command and write command to perform different types of analysis. M+, EQS, there are many other software to perform CBSEM. EQS and M+ are much more powerful compared to MOS, M+ and EQS. So if somebody wants to use CBSEM, it's better to apply this software. But MOS is very, very famous and popular in a different region, especially in this region, Asia Pacific. For PLSM, we have also many different softwares. Smart PLS and VARP PLS are two very common software and powerful software to perform PLS. Adanko is another software was developed recently by Jörg Hensler. Also, there are other software, XL Stata, PLS Graph, Visual PLS, PLS GUI, and other software. So you can apply different software to perform PLS. But the two first softwares are software packages are most popular and well-known to perform PLS. I try to show you how we can create model and perform in these two software, PLS, Smart PLS, and VARP PLS. So actually you can learn some basic things about these two software and how you can use and